okay, and this is the thing that might come up. So this is like getting to know G is a function of T and P, right? Because this is what chemists like, and for the reasons we talked about. There's a knob for T and a knob for P, and we want to talk about processes under those conditions. And remember, we got G by taking U minus TS plus PV. Because remember, this much of it was U minus TS is A, and then A plus PV is G, or we could have A plus PV or H minus TS, and so, but I call these things. This is not necessary to. I'm not going to say what is it like a term. Okay, so don't wish for things because they might come true. There could be a term, Legendre transform. Okay, but I'm not going to do that because that is what that is the mathematical thing. But we're doing these transforms to get rid of. Let's review here. We had U, which is a function of S and V, I claim, because du is TdS minus PdV, right? And then I said, okay, I could have H is equal to U plus PV, and then I got dH was T ds plus V dP, and the fact that I added PV to U, it canceled out the dV and replaced it with a dP, right? And then we had G, which was U plus PV minus TS, which would be also H minus TS. And we got, dG is minus S dt plus V dP. And of course, poor A, always gets left out, right? And the physicists, they like it, but I put them in the same category as engineers sometimes. Sorry to the engineers that are here. I actually like engineers. Some of my best friends are engineers in real life. Okay. So anyway, we had all these relations and all these. Okay. So look at the back page of your latest homework assignment, and I put there the useful and useless information updated. Okay, so that will be that's the kind of level of what you don't have to remember for the midterm. So that stuff will all be there for you, right? But we're pardon me. Where'd I do that? Oh yeah, what is that? What am I doing? Okay. I was up in LA visiting my son yesterday. We went to some dive bars. And there's a great restaurant called Spoke. Anybody from LA? You know that place? Yeah, okay. So it's along a bike trail, so people are supposed to ride their bikes there, right along the river. It's the kind of place that I'm sitting there with my son, and at the next table, there's some guy writing with some kind of fountain pen in a journal. Then the next table over, there's this young woman is also writing in a journal. It's one of those places. What is with that? They're thinking such deep thoughts there. But we lucked out because this is what happens when you have a bunch of hipsters working in a place. So you place your order, and then they give you your beers. And then about 10 minutes later, the buzzer goes off, and then they have your beers for you. So they gave us extra. I like it. LA's a great place. You know, it's fun going up there. Anyway, this is just to remind you, so you know, G, we got it by taking U and doing this Legendre transform, getting rid of S, which is awkward, replacing it with T, getting rid of V, which is use. You know, there's nothing wrong with volume, but we replace it with pressure because we don't want to control the volume always. It's relatively expensive. So I have my dg, right, and I have minus s dt plus v dp, and that tells me, we're still reviewing here, it tells me that these are the partial derivatives. Oh, this is p, okay, dp. Tells me what the partial derivatives of that function are. And so it tells me it tells me g dt at constant p is minus s, and it tells me that dg dp at constant t is v. And so if I draw a picture, let me just push it up so we can see those things. So that, you know, that's math, right? I mean, these are the mathematical consequences of this Legendre transform. But the beautiful thing, the thing that is interesting about science to me, is how the math and the physics, you know, they have this interplay, okay? And so this is telling me something about sort of the physical properties of G. So if I plot as a function of T and P, G is a function of T and P. So that's like it's like Z is a function of X and Y. If I was going to make a 3D map, right? I would have the landscape, how high the land is. Z is a function of X and Y. This is G as a function of T and P. And if I let's say so there's a surface. There's like a surface up there. And if I look at how the surface cuts, and I'm not saying this is P equals 0. This is just some arbitrary point. There's a slope here is less than 0 because the slope is minus S, right? So like if I go that way, if I hold the pressure constant and I look at how G depends on temperature, as temperature goes up, so this is up, this is increasing temperature, okay? As the temperature increases, G goes down. But if I go the other way, right, because that the slope is equal to V. V, volume is always positive, right, at least in this universe. And so that slope is up. And so I can draw this some sort of landscape that looks like that. You know, the picture is not very artistic. And we saw, and we're getting into this new stuff here, which I think Kyle already mentioned. I think I drew this picture already. So this is G as a function of T, and let's say P equals 1 atmosphere. I'm going to go down. So remember, let me write out my, what? Possibly. I mean, I can go back. Okay. Isn't that a beautiful picture? Okay, you got it? Good. So I'm going to draw. See this. So I'm gonna fix my pressure to be 1 atmosphere. I'm gonna look at, like, this might be 1 atmosphere here. Okay, so I might take that slice. Okay, so you know, visual. Some people are good at visualizing things, but my pictures don't help, right? Because they're not that good. But if I go and look at that slice. So this is T, and this is G as a function of T. and the pressure is 1 atmosphere. So and I drew this picture before. And so this is, it's got a negative slope. And so the question is, like, what phase of matter am I talking about? We're getting into these phase transitions. So the slopes are equal minus the entropy, right? And so I have 3 possibilities. I can have a solid, I could have a liquid, or I could have a vapor, or, you know, we could call that a gas. So there's an S of the solid, there's an S of the liquid, and there's an S of the vapor. And let's call this S of S, S of L, and S of G, just because I don't feel like writing so many subscripts. So entropy, are they positive or negative? Positive, right? And so which one is the smallest entropy? Solid, right? So S solid is less than S liquid, and it's much less than the gas, right? Because the gas is, you know, a liquid is like you know, I just didn't do dishes one night and the kitchen's a little bit messy. Whereas gas is like, well, for a whole year, you just left your DoorDash boxes everywhere, okay? So it's the apartment is a mess. And so if I draw these slopes, that's the solid. That's the liquid. And that one is the gas. And the question is, and so this is again a beautiful picture. And the question is, what phase of matter do I have under different circumstances? And you know this. You know, the spoiler is this picture explains, you know, why at this temperature the solid is stable, but if it's a higher temperature it's not stable, the stuff melts, and then the liquid is stable. What do I mean by stable? What is the most stable form? You know, something can undergo a process, and associated with that process is a change in all the thermodynamic quantities, right? And if that change can occur, and there's different possibilities at a given conditions, which state is the most stable one? What have they been telling you since high school, even before? The one with the lowest Gibbs free energy, right? So this, whoops. You know, you sit here and see, I know where the undo button is, so come on. So this is the lowest, right? Until I get to here, then this is the lowest. Until I get to here, then this is the lowest. So as a function of temperature, sort of work on my picture some more. There's a couple key points, and you know, we drew this picture. You know, this is the melting point. And this is the boiling point. And here we have a solid, here we have a liquid, and here we have, over here, we have a gas. Let's circle these things so the picture kind of makes sense. And so, by getting to know our G and knowing that, as a function of temperature, as I raise the temperature, G is always going to decrease. And sometimes it decreases in this non-continuous way, where some other phase, so there's like a hypothetical, it's not even that hypothetical, is it? Because we know that you can take a liquid, right? And you can, like, let's say you're careful. I mean, this doesn't apply to me very, very well, but if you're careful and you cool water down and you get to 0, and can you cool it down below 0 Celsius? You can, right? Or you can make a this applies to all kinds of things. Like you can take a saturated solution of something and you can cool it down. And then it's, what do they call that? Super saturated, right? And so it's sort of metastable, it's sitting there, but then you can come along and you can throw in a little seed crystal or something, and then what happens? Suddenly, stuff precipitates. You can. This is kind of dangerous. Right? You can superheat a liquid. Did you ever put something in the microwave, like a cup of water, make tea? You heat up the water in the microwave, and it's not boiling, But then you put your tea bag in, it just decides to boil. That's sort of being over here. Let me make sure I don't erase everything here. That's like heating it up, right? And then you're here, and then you put the tea bag in, and kabam! It boils. Okay, so you can push this, and one way you can think about this, and this is a little bit beyond the scope of the course. Let's say we went down. Let's say we went down that line, okay, versus going down. Let's do it over here. Let's say we look over here versus here. This is A, B. Okay, and then this point is C. Okay. Let's be sensible people. It's hard for me. A, B, and C. So we go in that order. And if I had A, there's some variable. I'm not saying what it is. I will say they would call it an order parameter, and you essentially have something that looks like this. So this is G as a function of let's say it's density. So rho is density, and maybe here this would be the liquid and the solid. So this is water. No, it's not water because it's some material that the solid would sink, so a higher density. And so there is some. It's like a reaction coordinate. You have something where if you were over here, you would be unstable, but there's a barrier to get over. So this is the stable form for solid. So at point A, you'd have this situation. At point C, you'd have this situation. So that would be stable. So the liquid would be solid. So it's free. Its Gibbs free energy would be lower. And at B, you'd have this kind of situation where the G of the liquid equals the G of the solid, and of course this is G. So it's like there's some sort of like double well going on, and you could imagine the situation where, and I'm not so it's as a function of the density. It's some sort of coordinate that describes where all the molecules are. If I have a lower, I could have a situation where I have a lower well like that. Then as I vary a parameter, this landscape kind of changes. And now this one's higher. But if I do it slowly and carefully enough, I can keep it trapped in there. And it's an activated process. I have to do something to it to get over the barrier. Same situation of having a picture like this. I talk about this because it's really a universal picture. This could actually be a reaction coordinate. I could have a balloon. If this were the good old days, I would actually do this. I did this back when I first taught general chemistry. Okay, do you have a mixture of hydrogen and oxygen in it? Okay, so if you take a balloon with just helium in it, and you put it up on a string, and then you have a match on the end of the on a stick, and then you hold it up to the balloon, and what happens? It pops, right? But now you put hydrogen and oxygen on the balloon. They don't let you do stuff like this anymore, and it's up there, and you come up with your match. This is what you do when people sleep. People don't sleep anymore because they're watching TikTok videos, right? Back in the good old days, people were better rested because of boring lectures. Anyway, you have that balloon with hydrogen and oxygen, and you bring the match up, and you bring it in contact with the balloon. What happens? Everybody wakes up, okay? Because it goes boom, like bam, okay? Now the SWAT team would come. They'd close the campus down, right? Anyway, you see what I'm saying. So why didn't it happen before the match? Because I had a situation where I had a pretty big a difference in these wells here. I was in a situation. Oops. I was in a situation like that, right? And then I put a match. And the barrier is lowered transiently, or something happens, and very quickly, I go down this hill. I'm not trapped anymore. Okay, and so you can have this. You can have a metastable thing. The world is full of metastable things like that, right? So and just be glad, because if everything found its thermodynamic minimum, that would be the end of everything, right? So we're all sort of trapped in a metastable state, and we can go about our business. And there's barriers to prevent us just going back to our most stable forms. But anyway, so that this is a useful picture. We'll come back to it. I keep saying things like that, but we will. And so I have this G as a function of T. And I'm not going to talk about this. It's in the book, and you can read about it. But I'm not going to say, okay, this is another. I'm not going to put as a term Gibbs-Helmholtz equation. That would be gratuitous. But there's something called the Gibbs-Helmholtz equation. The book goes through the derivation. Okay, read if interested. Read, what should you read? Book. What book should you read? Well, that's up to you, but you can read it in a textbook. Okay, so I'm just going to skip that. So let's look at G of T and P for, I don't know, let's pick a system to look at. I know. Let's do the ideal gas. Okay. You guys know a lot about the ideal gas, at least I hope you do. So I know that GT, partial G, partial P, at constant T is equal to V as a function of T and P, right? G is a function of T and P, so its partial derivative with respect to P at constant T, and then put the T back in, it's a function of T and P. So I think I mentioned this, like the fact that this is being held constant doesn't mean it's forever a constant, okay? You hold it constant while taking the derivative, but then it's back being a variable, and there it is in there. But the nice thing about this is, we know we know some stuff about the ideal gas. So I could calculate G of P by doing this. There's that calculus again, right? And hovering around T is a constant. Like if T is a variable, you could play a similar game to figure out. But let's just talk about this. So we're at room temperature or whatever, and we want to know what goes on. And there's a question on the homework that I just gave you. Isothermal reversible expansion of an ideal gas from V naught to 2 V naught. Surprise, surprise. Calculate delta G. Okay, so there's a couple ways you can do it. Delta H minus T delta S, for instance, that would be a good way. But another way is to do this. But then it's the pressure is the variable, but it's an ideal gas. So if I double the volume at a constant temperature, what happens to the pressure? Well, if I have a gas and I put it in a bigger box, I make the box bigger, probably the pressure goes down. But if it's an adiabatic one, it goes down, but a different amount then. If I do it isothermally, like if I double the volume at a constant temperature, the pressure goes down by a factor of, well, 2. Okay, it's 1/2 as much. Okay. So the temperature goes down by a factor of 1, I guess. I mean, that's not a good way to say it. The temperature doesn't change, but PV equals RT, right? So P times V is a constant. So if V goes up, P goes down, and by the same factor, except one in the numerator, the other in the denominator. But in general, we could do this, and the engineers would have some complicated formula for what it does for their product, like the petroleum product that they're getting out of their fracking or something. I don't know, something like that. But we're idealists in this class, so we'll use the ideal gas, where PV equals RT, and so V is a function of T and P is RT over P, right? And that's, for an ideal gas, that's always true. And it happens to be, we could do the adiabatic problem where we need T as a function of P, instead of T as a function of V. We could go through that whole, get those weird exponents with 5s and 3s and stuff, And then we could do a problem, but we're doing the more simple version here. And so, this is a constant for our problem. So my G of P is G of P naught plus RT, the integral from P naught to P dP over P. And I'm being a little sloppy. I'm using the upper limit as a kind of a variable, but I'm using the same variable in the integral. And so I might be tempted. I might do the integral from P naught to P of like dP prime over P prime. A math class might do that just because I don't want to call the upper limit the same thing as the variable, but I'm going to be sloppy because life is too short, and if I do the integral, what do I get? RT log P over P naught. So there we go. G of P equals G of P naught plus RT log P over P naught. I can check myself. If I put in P equals P naught, I just get G equals G naught. So my boundary condition here, or whatever, is okay. And so let's let's see if we can do this another way, or just look at that in the last few minutes. I know G of T and P, it's H of T and P minus T S of T and P. Also, I'll say also. So this is another true statement. I mean, I'm assuming that I didn't make a mistake. But, and this is one of the things about thermodynamics, that is part of its power and beauty, and also why it can be confusing, because, it's a multiply connected world you're wandering in. It's one of these video games where you can get from point A to point B a number of different ways, and there's different monsters, bosses. They've called them that for a long time, right? Do they still call them that? Yeah, okay. And you have to fight a different boss if you'll go one way or the other. But we can also, we could hopefully get the same result doing this, right? And H is a function of T and P. I know that it's a function of H of T only, right? So it's independent of, and for my C equals 3 halves, N equals 1 system, it's 5 halves RT, right? And S is a function of T and P. I can write down too. It's S naught plus R log T over T naught to the 3 halves V over V naught. But this is a function of T and P. So I got to be careful, right? Because I have a formula for S as a function of T and V that I worked out previously, and it's on the back of the exam, but there may be a little bit of, there's a little bit of added value that one has to put in there, because I know for the ideal gas, V over V naught, right, is RT over P times P naught over RT naught, right? So I'm just arranging things. So I have a T over T naught times a P naught over P. I gotta get it. I gotta get it in terms. That's bad grammar. I must endeavor to get this to be expressed in terms of the proper variables for the problem at hand. Okay, so I have to do this, and so my S of T and P is going to be S naught plus R log T over T naught to the 5 halves, right? Eraser. Because 3 halves, T over T naught to the 3 halves times T over T naught is T over T naught to the 3 halves times T over T naught to the 2 halves. And even back in Nebraska, 3 halves plus 2 halves is 5 halves, right? And so that's why it's 5 halves. Then I've got a P naught over P. Or I could write this as S naught minus R log. You're not going to see that log. You're going to, where did the log go? You didn't have a log on your lecture, and I left it off on the exam. I mean, what? You're going to hear from my lawyer. You're going to hear from my parents. They're both lawyers, right? Look, it could happen. 5 halves, minus, and then I can put P over P naught. Right, because I took log of 1 over x is minus the log of x, logarithm properties. And so if I define g naught as g of t naught and p naught, which is 5 halves r t naught minus t naught s naught, right? Then if I work out g of t and p, I get g of whoops. I get g naught plus rt log p over p naught. And notice I'm going up without even anybody asking. There's a minus here, isn't there? Right? And there's a minus here. And those two minuses conspire to give me this. So I get the same answer, okay? So I didn't have to have G, I didn't have to use this thing I learned about G. So I learned a lot of things. I learned that this is true, right? Then I used for the ideal gas, I could solve that. It's really a differential equation given to me. I solved it for G as a function of P at constant T. And then I said, well, there's another way to do it. I fought a different boss, which is this one. I don't know which one you like to fight better. But of course, and this is the key thing, if you do it right, and that's the big if, right? But if you do it right, then you can get from this point to that point by a couple of different ways, and that's where we got here. So now, if you know that, and it's the kind of thing that will be on the back of the exam, then you can use it, right? And so if I expand a gas, so what is delta G for isothermal V naught to 2 V naught, right? So I'm doing one of the problems, and it's reversible.